Hello everybody. Today we shall discuss about stars which will follow a little different equation of state. So let me start by reminding you of the stellar structure equations. And today we are writing it down in terms of R instead of M. Now, if you look at these equations are certainly coupled, which means that, say, if I want to know how the density varies with respect to the radius, I have to use this equation and this equation, but then pressure is unknown. So I need the equation of state to write down the pressure, but the equation of state as, say, the temperature. So I also need to involve this equation, but this equation has L, so I need to involve this equation. So all the equations has to go together. But if I have an equation of state which is like that of the electrons, which are in the regenerate gas form, then remember that the equation of state doesn't depend on temperature. P varies as rho to the power gamma, where gamma is 4 by 3 for the relativistic case, and 5 by 3 for the non-relativistic case. You see, something remarkably simpler happens now. So P is rho to the power gamma, so the first equation can be written only in terms of gamma. Only in terms of rho. And the other thing the first equation has is M, but if I use the second equation, then M can also be replaced in terms of R and rho. So I can just solve the first equation, two equations separately. I don't need to involve all the other equations. So in such cases, one can actually have analytical solution of this system of equations, particularly how the density depends on the radius, the pressure depends on the radius, etc. And that is what we are going to do today. Because P is given as rho to the power some number, these are often called polytropic equations of state. There is another parameterization, which is where gamma is written as 1 plus 1 by n, such that you can see clearly that the relativistic case gamma is 4 by 3 and n will be then 3, and non-relativistic case gamma is 5 by 3, which means n will have to be 3 by 2. Okay, so with this, let us see how can we combine the first two equations and try to get an analytical solution. To do this, so let me first write the first equation. We start with writing dp equals minus rho gm by r square. You see, for the second equation, I need a derivative of m with respect to r. So what I do is, I multiply these with r square by rho and then take a derivative. So this is what I am applying on this. So let's see what way I get. I get ddr of r square by rho dpdr in the left hand side. In the right hand side, I have rho by r square, that cancels r square by rho. I get minus g, and then I have dm dr that I can replace from the second equation here. dm dr is 4 pi r square rho. So I need to do a little bit of algebra today. I take the 1 by r square in the left hand side. This looks almost like a Poisson equation, but remember that the left hand side I have p, right hand side I have rho. Now p I can write in terms of rho. So I write p is k into rho to the power n, which is, sorry, rho to the power gamma, which is rho to the power 1 by 1 plus n. So if I do that, then this becomes 1 by r square ddr r square by rho dpdr will be k one plus 1 by n is n plus 1 by n. When I take the derivative, the power reduces by 1, so rho to the power 1 by n, and then I'll be left with d rho dr. Now let's collect all the constants together outside. So I have n plus 1 times k in the numerator, and the denominator I can bring 4 pi g from the other side here, and I have n. Then I am left with all the variables. R square. The entire row dependence I can write in the denominator. So this is rho to the power 1 minus 1 by n and d rho dr. Right hand side 4 pi g is gone, so I'm left with minus rho. So this is my equation, and it's the equation of rho, so I can just solve rho as a function of r in principle. So the solution will be rho as a function of r. For that I will need the boundary conditions. So what are the boundary conditions? Set r equals to 0. See, r is a radial coordinate. R equals to 0 can be approached from different angular directions. So it is better that at the center everything should be smooth. Also that the rho is 0 for whatever direction you approach at the center. So this is d rho dr should be 0 at r equals to 0. And at r equals to capital R, what should be the rho at the center? Sorry, at the surface. The surface rho should be 0. That is, these are the boundary conditions. So it's complicated boundary condition. One is given as Neumann, one is given as Dirichlet. So it's a Cauchy boundary condition if you consider all of them together. Now what will be the parameters here? Whatever the functional form is, it will depend on the parameters. The parameters are, I have n and k. Capital G is a constant, it cannot be a parameter. N and k are the parameters which I have in this. And because the boundary conditions has capital R in it, that will also be a parameter. So the solution will have these three. Okay, so now let us simplify this equation a little bit, and we will write it in a dimensionless form. So what we do is, at r equals to 0, the value of rho, I can call it as rho c, critical density, core density, sorry, not critical, core density. And we assume, this assumption need not be correct, but it works out here, that rho at any radius can be parameterized this way. Okay, so we can see theta is dimensionless. Rho and rho c has the same dimension. So it's a core temperature, sorry, core density times some theta to the power n. So this is what I will like to substitute in this expression and see what happens. So let's do that. Rho to the power 1 minus 1 by n will be rho c to the power n minus 1 by n, and then theta to the power n minus 1 by n, which is essentially theta to the power n minus 1, because I have a power n over here, theta to the power n over here. Let's do the derivative. If I do the derivative with respect to r, I'll obviously get the rho c, and then I will get theta to the power n minus 1 and d theta dr. Right hand side is obviously minus rho c theta to the power n. Please do it yourself and check what I am doing is actually right. So what do we get here? You see, theta to the power n minus 1 gets cancelled out, and I have rho c to the power n minus 1 by n here, which I can take out. The rho c in the numerator can be cancelled with the rho c in the right hand side. So what I get is 1 by r square ddr of, I've taken care of all the constants, so d theta dr equals minus theta to the power n. Let's look at the dimension of different sides. So this is dimensionless, theta is dimensionless. Here, first term is L to the minus 2, then L to the minus 1, then r square is L to the 2, and then again I have L to the minus 1. So the full dimension here is L to the minus 2, which means this entire quantity has a dimension of L square. So what I do is the following. I define n plus 1 times k by 4 pi g n into 1 by rho c n minus 1 by n. This entire quantity equals alpha square. Just I redefine this quantity, I call it alpha square. This have a dimension of L2 length square. And then I define further a dimensionless radius, if you wish, which is r by alpha. Xi is dimensionless. Okay. So what will happen to my equation? I need a little bit space here, so let me make some space. So the equation becomes, so let us keep this in cloud. This is alpha square, which is this entire thing as I define. R square is xi square alpha square. So I get 1 by alpha square xi square here, and then 1 by d of xi alpha. Remember, alpha is just a constant. You see, there are as many alpha in the numerator as in the denominator, so they got cancelled out. What I will be left with at the end of doing all this circus is 1 by xi square d d xi xi square d theta d xi equals minus theta to the power n. And let me remind you what are the different things we have assumed. I said rho is the core density times theta to the power n. This n, by the way, is the same n that I have in my polytropic equation of state. It's not a different quantity. We defined alpha square to be 1 plus n k by 4 pi g 1 by the core density to the power n minus 1 by n. Let's call this alpha n because this will be different for two different types of polytropes. And our definition of xi is that R equals alpha times xi. Now this is what I have. Once I have done with all the circus, this is the final thing that I have had. This equation is a very important one for polytropic equation of state stellar structures. This is called Len-Endem equation. And this can be easily solved. You can even use a computer to solve this. What are the boundary conditions? So that is also another important thing. So we consider that the stellar radius of the star, which I call capital R, is the radius of the star. This is alpha times some value of xi, called xi1. Okay. See the radius we have scaled, and when xi equals to xi1, I reach the surface of the star. So that is the stellar radius. So at here at xi equals to 0, R is also 0, and from the previous condition of d rho dr, we will see this will also be 0. What about theta? Theta will be 1 at xi equals to 0. Because at xi equals to 0, what is the value of, xi equals to 0, rho is equals to rho c, which essentially tells me that xi equals to 0, theta has to be equals to 1. Fine. So these are the boundary conditions. So let us see what happens if I solve this equation given these boundary conditions. This is a solution where I plot small r by capital R in the x-axis and rho by rho c in the y-axis. There are two curves. One corresponds to the non-relativistic case, the other corresponds to the relativistic case. At the center where r equals to 0, rho equals to rho c, so the maximum value of rho by rho c is 1 there. On the other hand, at r equals to capital R, both of them goes to 0. The density obviously, beyond this radius of the star, there is no density. We observe that the relativistic case, more mass is at the center or at the central part of the star. Alright, let us try to calculate how can we write down the expression for the total mass of such a star. How do I calculate the total mass of such a star? It is very, very simple. Now change the units to alpha and xi. R is alpha times xi and rho is pc times rho c times theta to the power n. So R, there are three of them. I'll get alpha cube, which I can take outside the integral, so as rho c. So this will become xi square theta to the power n and then d xi. So I have xi square theta to the power n d xi here. I have theta to the power n here, and the xi square, if I bring in the right hand side, I just get d d xi of xi square d theta d xi. So this essentially becomes 4 pi alpha cube rho c d of xi square d theta d xi. One thing I did not do, when I change the units from r to xi, remember that this should go to xi1, which I said is the radius of the star, corresponds to the radius of the star. And the Lennard equation has a minus sign, so I should have a minus sign here. So what do I get? I get the mass of the star as minus 4 pi alpha cube rho c. Xi1 is 0 at when this quantity has to be evaluated at xi1 and 0. When it is 0, this quantity is 0. So this is just xi1 square d theta d xi evaluated at xi1, which is at the radius of the star. So in this plot, what is the derivative at this place is what you are asking. So let me put this in box, because this is another important thing which you will be using shortly. Now remember, my alpha times xi1 is the radius of the star. So I should be able to get a relationship between the mass and radius from this particular expression. Before I go there, let us calculate the average density of the star. Average density I call rho bar. This is simply mass by 4/3 pi r cube. So let us write m in terms of r first in the numerator. So I will have 4 pi alpha cube is r cube by xi1 cube, which I will write shortly, rho c, and this is xi1 square. I had a xi1 cube there, so this is xi1 to the power minus 1, and 4 by 3 pi r cube here d theta d xi at xi1. So see, what I get is rho bar is r cube etc. cancels out. Xi1, remember, is a dimensionless number. So this is just 3 by xi1 and d theta d xi evaluated at xi1, that's also a dimensionless number, times rho c. So rho bar is directly proportional to rho c for this polytropic cases. So that is the conclusion from the calculation of rho bar. Okay, now we have been writing, we have written down here the mass in terms of alpha cube. So I have m, as we have written, as 4 pi alpha cube rho c xi 1 square d theta d xi at xi 1. And remember, alpha square was given by n plus 1 into k, and this depends on n. This k should also be written as a suffix n, because that will change if I choose different two different types of equation substrate. Just remember that I am not writing it explicitly here. So these two I had. Let me remind you that we had these two earlier. I am not writing it from the sky. This is the expression for the mass. And this is the expression for alpha n. The expression for alpha n, I can revert to write an expression for rho. So the critical density using the expression for alpha n, I can write as n plus 1 into k by 4 pi g So I can write this as n plus 1 into k by 4 pi g whole to the power this n by n minus 1, and then alpha n to the power 2n by 1 minus n, because alpha n square was in the denominator. Alright, so I got rho c in terms of alpha n. And why I am doing this? Well, I have the mass here. This rho c I can replace in terms of alpha. What we want to arrive at is a relationship between mass m and radius r. Okay, that is what we are trying. So if I write the mass now, I have 4 pi, and then from this rho c I will get n plus 1 into k by 4 pi g. This is a dimension full but constant number which depends on n, whether it's relativistic or non-relativistic degenerate gas. And then remember that I had here alpha cube and then rho c xi 1 square d theta d xi. So alpha cube will become, this will become 3 plus 2n by 1 minus n. So that entire thing is alpha cube rho c. And then I have xi 1 square d theta d xi at xi 1. Now this is a number. This is a constant, dimension full. This is obviously constant. And we know that alpha n is r by xi 1. Alpha n is given by that. Again, xi 1 is dimensionless. R is the radius. So we get now that the mass and the radius has to be related this way, r to the power, so 3 plus, let's do the math here, 3 minus 3n plus 2n, which is 3 minus n by 1 minus n. Or more precisely, I can write it in the following manner. M by mn, let me write and then this will be clear why I am writing it this way, to the power n minus 1 is equals r by rn to the power 3 minus n into n plus 1 times k by 4 pi g If you work it out, you will see what you get here is, including all the constant, is gm by mn whole to the power n minus 1 times r by rn whole to the power 3 minus n equals n plus 1 k by 4 pi g I guess only this much to the power n. And mn and rn, this will depend on this quantities xi1 square, d theta, d psi, etc., which depends on which n you are talking about. That's why you have kept n over there. Okay. So this is the mass and radius relationship for polytropic equation of state. Now let's see what happens for non-relativistic case and relativistic case. Non-relativistic case, what is the value of n? N is 3 by 2. So gm by mn to the power 3 by 2 minus 1 is half, is r by rn. 3 minus 3 by 2 is 3 by 2 itself, equals so if you get rid of the half from all the sides, you see that m in this case, these n's are basically 3 by 2. This I can also put in 3 by 2 over here. So m will go as r to the minus 3. So for such stars, the radius goes as r to the mass to the minus 1/3, which is mass is a parameter, so the radius will change with this parameter this way. So the core temperature at the near to the center of the star, we saw that this goes similarly as the average temperature, and the average temperature goes as the mass r to the minus 3, which means this is r to the m square. So for these stars, non-relativistic stars we are talking about here, the core temperature, the core density goes as m square. Okay, so this is non-relativistic. Let's see what happens for the relativistic case. Relativistic case, n equals to 3. So let's put n equals to 3 everywhere here. So I get gm by m3 to the power 3 minus 1 is 2. So gm by m3 square. R by Rn is to the power 3 minus n. Now n equals to 3. R by Rn to the power 0. That will not come. What all I am left with is 3 plus 1, 4 here. So 4k whole cube by 4 pi g. Now m will be equals to interesting thing is that this does not depend on the radius of the star. There is only one possible value of the mass. There is only one value of the mass if the star is stable. Obviously, we are using the hydrodynamic stability criteria. Okay, so now let us look at what is happening. Imagine that there are many stars which are all having relativistically degenerate gases. Okay, sorry, which are all having degenerate gases. Now, if there are stars which are relatively smaller mass, for which it is the gas is non-relativistic. As you approach to the higher and higher mass stars, the density at the core increases as mass square. But then there is a certain critical density over which if you go, then it will not remain a non-relativistic degenerate gas, it will become a relativistic degenerate gas. And then this happens. Once you reach the mass for which it's a relativistic degenerate gas, it turns out that there is only one mass for which the gas is stable. So that mass is called the Chandrasekhar mass. So Chandrasekhar said that this is the limiting mass of a white dwarf. The white dwarfs, if they have non-relativistic degenerate gas, their mass can keep on increasing, but then at some mass it will become relativistic And then the only stable mass, only star which will have a stable dynamical stability satisfied can have this mass only. And this mass, let's write in a little different way. This is derived from what we are talking about here only. And what is done is that M3 is kept as M3. That will depend on some properties of the star. And this K is substituted back. That K is also supposed to be K3. And you get this expression. This I am not deriving. This is for, so this can be written putting the value of these constants. This comes out to be 5.83 mu e to the minus 2 in terms of solar mass. If mu e equals 2, which is if the composition is of helium, carbon, oxygen, hydrogen, obviously, etc., then MCH is divided by 4. So this becomes 1.46 solar mass. So that is the Chandrasekhar's limit, for which, so this was discovered in 1931, and he got the Nobel Prize for this in 1983. See, more than 50 years for people to believe in this theory. So that concludes our discussion today. We looked at the polytropic equation of states for the degenerate gases, where the pressure only depends on density, and we went on calculating a very important limit, which is the Chandrasekhar mass limit, which tells you that if there is a relativistically degenerate gas, there is a maximum mass over which such a degenerate gas star will not be stable, hence will not exist.